to go with a gentleman that I know fairly well, Mr. Paul Bony. Paul became involved in geothermal heat pump industry in the late 1880s as a utility program developer. Prior to joining Climate Master, he managed the development of several innovative utility financing tools, including GHP, ground geothermal heat pump, loop and equipment leases, CO-Z, which maybe you can explain, energy plan, and a groundbreaking geothermal loop utility tariff. He has also provided legislative and regulatory testimony on GHP programs and financing to committees of both the U.S. House and Senate and numerous state legislators and regulatory agencies. With that, Mr. Paul Bony.
Thank you. The pronunciation is cozy, not C-O-Z, but it could be C-O-X, so no C-O, right, or C-O-2-X. And I am old enough, I was on the original California Energy Commission Geothermal Working Group. So here we are 20-some years later, and we're still working towards getting into Title 24. So hopefully it will be more successful this time. So I want to start off, and a lot of this is fortunately repeat, so I can expedite the conversation a little bit. But if you stay with the true zero net energy building definition that says over the course of a year you're going to be fossil free and you're not going to use more energy than you consume, that obviously takes us out of the fossil fuel realm. You've heard that you can be fossil free in Quincy, California, which is pretty cold. You don't have to take my word for it, but back in 2012, after a big study, the New Buildings Institute said, yeah, we can do that with off-the-shelf technology today. And that's really the key. We don't have to invent anything to get to true ZNE. We just have to deploy the technologies we have. And then there was a question earlier in the audience, and I want to address that, especially as relates to moderate climates. I also want to say if you're going to follow the Amory-Lovins model that says we want to value engineer to the lowest cost solution, ground source heat pumps, because of their efficiency, can reduce the investment you need in renewable energy generation, so the total system cost actually comes down versus other heating, cooling, and water heating options. And then I want to talk a little bit about there's really the technology. Ground source heat pumps are not static, so the latest generation of equipment actually can turn your water heating load down to about a kW of PV electric can drive your water heating for a family of 4 for a year. So think about that. A 1 kW PV system on average across the country can make the domestic hot water for a family of 4 over the course of a year. So that's a huge transformation. And it really boils down to how do we get that CO2 out of the equation, and you can't burn methane, you can't take a carbon fuel and burn it and not release CO2. So true ZNE, carbon-free, the two things the state of California are driving to is really available today with off-the-shelf technology. And Governor Brown addressed this just last year in one of his speeches. He said it was going to be hard, right? And Governor Brown said this is going to be hard, but we have to make this transition. And I think there's partnerships that need to be developed in the state. I don't want to name any names, but I was with some utility folks the other day, and they said, well, this sounds hard. And I'm like, okay, it's going to be hard. But did Edison look at when he invented the electric grid? Did he say, oh, I don't know if I want to invent the electric grid to sell light bulbs because that's going to be hard, right? He just went out and invented the light bulb, right? He failed 1,000 times. That wasn't easy. And when people said, did those disappointments, affect your motivation? He said, no, I just found 1,000 things that didn't work, right? Then he invented the light bulb, and he built the electric generation system to sell light bulbs. So I think it's really not that hard to transition the way we use energy in our economy. You've seen the formula, an energy efficient envelope plus a renewable energy system. We say combine it with a super efficient ground source heat pump. There are places where an electric air source heat pump or a compressor driven system will work just fine, just as passive solar thermal will. And the goal is to get to that energy consumption on site that equals your use. And for those, the public utilities are starting to say, wait a minute, there are buildings that won't have enough roof, or there's trees, or there's other options that prevent the on-site generation. Why don't we expand the definition of ZNE so the generation is at least really close, right? So you have your community solar garden, Maybe it's 5 blocks away, but those kilowatts are still going into the neighborhood, the whole microgrid concept. So you don't have to tie the PV to the building, but if you can, great. You can tie wind to it. And some are saying when the grid is carbon-free, right, if there's no carbon in the kilowatt hours, why are kilowatt hours bad to dry carbon-free heating, cooling, and water heating? So we really have to get our mind around the focus that kilowatt hours were easy to pick on when they were perceived as all coal-fired and dirty. All of our energy efficiency programs, and I've been started in demand-side planning 20-some years ago, it really was, can we save customers money versus the next incremental investment in power plants or the grid? Then it became, can we decarbonize the economy? And that's really where the focus is now. And I'm saying with off-the-shelf technologies, we can do both. Oak Ridge in 2010 did a nationwide what-if study, kind of what we saw earlier from Mark. And they said if we could convert the economy to ground source heat pumps, we'd knock the energy consumed, now energy measured in therms, not kilowatt hours, not BTUs, but thermal energy, by 45%. We could clip utility peaks by 56%. We could reduce customers' bills by 48%. And we could reduce carbon emissions in the U.S. economy by 45%, right, with one technology. And that's before we look at all the other things we've talked about today, lighting, thermal shell, better windows, better appliances. This pie chart really sums it up. You put a ground source heat pump on a building that otherwise would have used conventional gas furnace, gas water heater, standard air conditioning, and you can knock about half of the thermal loads out of the building by coupling it to the earth. The biggest piece of the pie is still heating and cooling, followed by water heating, but look at the slice that's left. It's lighting and appliances. And this chart was developed before LEDs, right? So we can shrink the LED part, or the lighting and appliance part. The hot water on that chart at 6%, this was based when ground source heat pumps could only make hot water when they were in air conditioning and then supply a little bit when the compressor was running and heating. The current generation of equipment can make domestic hot water at the fully rated efficiency of the compressor at that entering water temperature. So now we can make full load domestic hot water at efficiencies of 500%. So that 6% slice can probably go to 2 or 3%. And it's really this simple. By coupling the building to the ground or to a thermal source of water, and I'll talk a little bit more about that, 1 kilowatt hour of power can deliver 4 to 6 kilowatt hour equivalents of thermal energy, whether it's heating or air conditioning. And the balance, it's not magic, you're just leveraging energy out of the ground. So a compressor is a lever, takes a little bit of energy to run the compressor and the pumps to deliver a large amount of thermal energy. And it's a little piece of bent copper that makes that happen. That's called a coaxial heat exchanger. That's the heart of every water source heat pump. If water goes one way, the refrigerant gas goes the other way. In heating, you pre-warm the refrigerant gas so the compressor doesn't have to work very hard to pump it up to a high temperature usable state. And in cooling, you dump the heat into the water, put it back into the ground and cool it off again so the compressor doesn't have to work as hard to try to blow this hot gas out in whatever the outdoor air temperature is. So a very simple concept, water reacting with refrigerant in a closed environment so they don't actually mix, they just see each other thermally, drives those efficiencies. So a very simple process, connect the building to the ground, drilling backhoes like Bill did. I'll show you some other options where you can directly interface with lakes and ponds and rivers and swimming pools. Once that thermal connection's made with some black pipe, and I have some samples of both the coax heat exchanger and the pipe in the back of the room, so come by and see those. Eventually you get 2 lines into a building, one for the water to come into the heat pump, do its energy exchange, and the other line so it can go back into the ground and do that thermal exchange. And that's all it takes to heat and cool a building with renewable thermal energy from the ground. These 4 pipes in the ground are the heating and cooling system, right, the energy source for a 6,000 square foot home in Denver, Colorado. So their comment earlier was, what do we do in urban spaces? I will tell you, one of those loops in Palo Alto will probably do a 1,400 square foot house, right? So you don't need a lot of space. And we had to shorten our presentations. There are drillers who have rigs that'll walk down the stairs into the basement of a building in New York City and drill through the foundation. There's equipment on skids. You open the gate or take one section of fence down and the driller can get in the backyard and put those loops in. So space is really, really not the consideration. You've already got the land under the building. You might as well use it. I have a friend who likes to say, Doug Rye, who's been promoting geothermal for years, you're already paying for a geothermal system. Why don't you have one? What does that mean? Well, if your energy bills are already high and you converted that into an annuity, you're really paying for the geothermal system. You're just not getting it because you might as well take your money out and burn it, right? And I live in a very conservative part of Colorado, so I have some very conservative friends. Some might say they belong to the Tea Party. And I say, do you like taxes? And they go, heck no. I said, do you like taxes that are wasted on programs that deliver no benefits? And then they get all red in the face. And I say, so why are you paying your utility for energy that you don't have to use? And then they spit and sputter and they don't invite me out for beers again. So we have, and I'm on the board of directors of Solar Energy International, a solar trading firm, and started doing solar systems as a utility guy 20-some years ago as well. Solar went from, remember how expensive solar was in the early days? $18, $20, $24 a watt?
Jingling.
Oh, I'm jingling. Okay, no jingle. So now solar, as you saw in the charts earlier, are really at grid scale in volume, and residential customers, a third of the country currently, their solar systems are about the same as grid power. So you've got solar, you're making electricity on site. What hasn't been talked about today is there's a bunch of folks, the solar industry is not static either. There are companies out there that have said, wait a minute, we've got the photons making electrons, but we're also making a lot of heat. So there are these next generation solar companies that are called solar cogeneration. This is just one sample. If they start capturing the thermal loads of those solar panels that get hot, they do two things. They make the solar panels more efficient, and now they've got thermal loads that they can capture, right? And they may not need all of the thermal load that they make at a point in time, but if they could just store it for a couple hours, for a couple of days, for a couple of weeks, then they can reduce the building's energy footprint even more, right? So these solar thermal guys enable ground source heat pumps to store thermal energy in a tank, basically a body of water, and you heard the number, $1 a kilowatt hour to use this thermal storage versus $600 a kilowatt hour to use a battery. And now we can make heat during the day, and I'll use Colorado as an example. In January, the sun's shining. We can make electricity and thermal energy during the day in Colorado, store the thermal energy, and these heat pumps, the warmer they're entering water in the winter, their efficiency isn't 5, it might be 7, right? So the warmer they're entering water, the more efficient the unit is. Conversely, if the wind's blowing at 2 in the morning, that heat pump can come on and pre-chill water when there's an excess of electricity. And there are markets where the utilities are paying people to take their power, right, because the wind guys still want to get their tax credits. You could run that compressor, pre-chill a volume of water, and then at noon to 4 when electricity is expensive, that heat pump isn't seeing 60-degree entering water and running at an EER of 30. It could see 30 entering water and run at a double EER. So ground source heat pumps are the only heating, cooling, and water heating technology that can store energy. The next advancement, this is a smart tank, the old dumb electric water heater that converts a bunch of kilowatt hours, 4,000 or 5,000 kilowatt hours a year into showers, is now a smart tank that can interact with the compressor and do that water heating for 1,000 kilowatt hours a year, right? So the market has not been static. PG&E calls this the grid of things. Ground source heat pumps are really computers inside heating and cooling systems now. All of these units from all the manufacturers are really computer chips in a heating and cooling and water heating technology that can now interface with the grid. They can run the I'd love to get into a little more detail. They can run and basically be told, you don't have to shut off because we're at a peak demand system. Why don't you just run at 30% for the next couple hours? So the decay and comfort for the homeowner isn't as much, right? It's not on off. That was our only choice back when we did load control. Now it's why don't we just run at low speed for a while? Or why don't we turn on now because electricity is very inexpensive and we want you to preheat or pre-chill this reservoir of BTUs. So the ground source heat pumps are totally digital. Next generation products, the pumps, the compressors, the fans are totally digital, totally computer controlled, and can interact via the web of things to become a truly interactive heating, cooling, and water heating system. So let's talk for just a second about the Duckzilla, right? The horrible duck of California energy markets. It basically says when the PV systems and the wind are blowing, the grid the grid needs no electricity because everybody's making their own. The sun quits shining, there's this snapback, which is the neck of the duck. And so we've got this system problem that we don't know how to get around that. It's hard. Well, if you start storing thermal renewable energy with compressors in a water bath, right, which means you need a water source heat pump to store it and harvest it, I like to say you can fill the belly and wring the neck of the duck, right? And you can't do that so much with air source heat pumps because you can't beat physics. The simple physics of the matter is air source heat pumps and air conditioning will always have a higher EER, a higher energy efficiency ratio than air source. And we have done this game as a society. The regulators adopted this, and it was basically Energy Star through the Department of Energy. We let manufacturers game EER into SEER, Seasonal Energy Efficiency Rating. I may be the only person in 5 counties who's read the entire regulations, right? It's over 1,000 pages in the Federal Register to tell you how to test for SEER in a laboratory at conditions that don't exist in the real world. So when it gets hot at 100 degrees in Sacramento, the true EER of an air conditioner has no relation to what its SEER was at tested conditions. They decay. That's why the neck is so steep on the duct. Ground source heat pumps only see their entering water temperature, and even if the entering water temperature gets to 110, right, which we don't design for, the EER of the ground source is always going to be well above the true EER of an air source equipment when people want to use it, right? When people want air conditioning, they don't care that that's a 13 EER unit at 70 degrees because the windows are open. When it's 105, the windows are closed and that unit is not performing at its nameplate rating. So in Sacramento, a 4-ton ground source heat pump versus a high EER or baseline SEER machine of 10, 4 tons of air conditioning, a ground source heat pump will knock off 2.5 kW of peak demand. That's the neck of the duck, right? So that's when I say we're going to wring the neck of the duck. We can do that just by equipment. So let's go into the PV versus geothermal heat pump just real quick. So I've done this analysis for Sacramento, so it's on the top. If you start with a high efficiency, now let's just say you want to build a true net zero house. So this is the base assumption. A high efficiency air source heat pump for heating and cooling, and an electric dumb water heater for water heating, right? Because you only want to use electricity because you're only going to make electricity on site. It would take a PV system just for the heating, cooling, and hot water, and you can see the kilowatt hour assumptions there. You'd need about a 5.7 kW PV system to meet those thermal loads, okay? I like to use PV watts off of NREL sites, so that was the software I used. Now, let's put in what we call an old ground source heat pump, or basically the current generation of contractor 2-speed compressor like Bill put it, right? High speed, low speed. You can see where the heating kilowatt hours go way down from the air source heat pump. The cooling kilowatt hours go down, though not as dramatically. And because you're making hot water when you're running the air conditioning and a little bit when you're running the heating, you lose some kilowatt hours off of what we call the desuperheater. So now a 5.7 kW system becomes a 3.9 kW system. At $3.70 a watt, you save $6,000 of PV to put in the ground source heat pump system. So this is a 2-ton system. That's about $3,500 a ton. That doesn't pay for the ground source heat pump system, but you also aren't paying for that $8,000 or $9,000 air source heat pump to go with the. So there's some deductions there. Go to the next generation where the compressor makes the hot water, because that's where the last big loads are. Now you're going to knock that PV to do your heating and cooling and water heating from 5.7 kW to 1.6, okay? And that puts almost $15,000 on the table to put in the a 2-ton ground source heat pump system. So add $8,000 in there, you could have a $24,000 ground source heat pump system and break even on what you would have spent on PV. That's $12,000 a ton. That's at least 2 times the national average, if not more, right? So you can have a really nice geothermal system and pay for it by not buying the PV system. The PV system will wear out in 30 years. The panels will eventually wear out. The inverter will have to be replaced. The biggest cost in that geothermal system, the loop, will be there 100 years from now, right? So after the loop goes in, the only thing left is equipment replacement, maybe every 27 to 30 years. I live in Colorado, so let's go where it's cold, right? So now it's cold. Air source heat pumps don't do really well when it's cold. Bill talked about the defrost cycle. So now you've got a $35,000 savings in PV to meet that thermal load. So we can sell you some really nice systems. Anybody in this room, you got $35,000 and want to buy a 2-ton heat pump system, we'll all talk to you, right, guys? Bruce especially. And then I picked Seattle because I'd done the analysis there, and it's kind of like this Bay Area climate. There's some differences. You still have a better spread in Seattle than you do in Sacramento, again, because the savings are there for the water heating, and are in the geothermal, because there's no air conditioning to drive the water heating unless you take it to the compressor. So in carbon terms, that ground source heat pump, and this is a 4-ton example, will save more carbon than 3 Teslas, right? And we saw the Teslas; those were $120,000 a piece, right, Bill? Yeah, the one I looked at was $120. Yeah, I was calling Visa to see what my credit limit was, but and that's actually the hybrid electric. So hybrid electric car, PG&E's calculator says 3,000 pounds of carbon a year if you drive by 12,000 miles. The geothermal plus the PV saves almost 3 times that. There are thermal energy sources out there right now that we're not taking advantage of. PG&E has 3 million pools, according to their own study. Every one of those pools in a moderate climate is a condenser and a cooling tower, right? So the people and most pools, even in Sacramento, a pool needs heating 12 months out of the year. So imagine if you air conditioned your house and then made your pool more swimmable all year round, right? And you didn't have to buy gas to heat the pool. This other one is a Canadian company. It's called the Shark, and they've come out with a little brother called the Piranha. So they estimate Americans flush 350 billion kilowatt hours a year down the toilet, right? So what they're doing is they basically capture sewage flow at strategic locations, take that thermal energy, put it back into the building. And how much did the loop cost when it's basically a garbage disposal on a sewer line that was already there? Right? So we have energy flowing to the sewer treatment plant that we don't capture. And then lastly, and this is a picture out of California, they've got the PV. The rest of their heating and cooling loads are 30 feet away in that body of water that could be extracted, what we call a lake plate, right? So we just need to open our eyes. You don't have to drill a hole in the ground to use a water source heat pump. Commercial buildings enclosing chillers versus rooftops versus ground source heat pumps. These are, case studies over the years. 25% more efficient than what we call packaged equipment, and that's really that number is actually bigger when you meter it. 50% more efficient than air coolers. So if you want to get to a net zero commercial building, you really don't want to combine those PVs to that air chilled cooler. So it's like Diane said. Look at the efficiency first, and then you can use the rest of your money to buy the renewable energy generation you need to get there. This is the American Society of Heating, Refrigeration, and Air Conditioning Engineers' own building. One-story geothermal. The other story is what we call variable speed city splits, variable speed refrigerant. So again, the ground source heat pumps consumed about half the kilowatt hours of what's been touted as the most efficient new thing for commercial space. Here's just a couple of quick examples, and the slides will be available so you can read these at your leisure. The Sierras Club's net zero building in St. Petersburg, Florida, solar and ground source heat pumps. Lady Bird Johnson School in Texas, where it gets really hot, 105 geothermal heat pumps. And so when we talk about AB 32 and the drought, California, this stuff really wasn't happening until this year, right? When you have 1 year's worth of reservoir storage, you really need to start paying attention to your water. Ground source heat pumps are not a consumptive use of water. Buildings with this building, when the windows are closed, this is really using a giant swamp cooler, an evaporative cooler, to air condition this building in the summer. How much water? Well, if you have a standard cooling tower, right, I forget the size of building this will go with, but this is about a mid-grade cooling tower, is consuming 15 million gallons of water a year just to evaporate to make cooling. Plus, when the water evaporates, it gets higher and higher in salts and minerals, so then you have to flush that down the sewer and start over again with a fresh batch of water. And then if the wind happens to be blowing when the cooling tower's on, all the mist that doesn't cool and go back into the pan, that's consumptive use of water. So we did a quick study with a fellow who used to sell chemicals into that business. We think there's 10,000 cooling towers of that last size in California. If those became ground source heat pumps, you could have half of Lake Folsom a year to serve people domestic water, which is basically somewhere between 1 and 2 million Los Angeles a year of their domestic water supply. So we're evaporating that much water to cool buildings when we don't have to, plus the energy to pump that water. So we fit the state's political goals. We're an off-the-shelf technology. We feather in nicely with thermal electric energy and with PV energy and wind energy. So those basically the points I wanted to make. I had minus 10 minutes to get us back on time, so I don't know if I pulled that off or not.
You did a fantastic job. Paul Bony.